a researcher exploring how low-resource languages, like Georgian, can thrive in the AI age through cutting-edge transfer learning methods. Here comes Beso Mikaberidze.
Hello. I'm Beso Mikaberidze, and my slides are not so dynamic. We have no videos. It's classic academic slides, but yeah, it is what it is. Today we will talk about artificial intelligence, but not about how to use it or what it can do, but about how we build it and try to improve. So the thing is that after 10 years of production engineering, now I have a luxury to do a research too, and this is really cool, especially when you collaborate with great people such Temo, Sahinadze, Simon Osterman, Philip Mueller from different universities such as BFKI, Max Planck, Muskhelishvili Institute, and others. So let's dive in. And the fact is that NLP, natural language processing, is evolving really fast, but low resource languages are far behind. And you can see the gap actually on this map, where these squares represent the size of NLP research in the particular language. But there is no Georgian here at all. Even though Georgia is not a low resource language, it is considered as mid-resource language. And when we are talking about low resource or mid-high resource, we just mean how much digital text do we have in that language, not literature. So, yeah, the goal of our research is to somehow help to narrow this gap. And first of all, to see the big picture, we impact in two main stages. They are tokenization and model adaptation. While tokenization is splitting all the text into several pieces, during language modeling, the system is learning the general language patterns based on a large amount raw text. And finally, we want to adapt this general language model to some real-world applications. To be more specific, we address two challenges. First is tokenization choice for Georgian language, where we investigate different existing approaches for our language. And second is limited resources, where we try to apply parameter-efficient transfer learning methods across 200 languages. But let's focus first on Georgian and on tokenizations, which is really hard for our language because it's grammar and rich morphology. Yet we could not find any study or papers about this topic. That's why we decided to do it and create one ourselves. And we evaluated 13 different tokenizers on 4 Georgian NLP tasks. And how we did it is that we went through all these 3 stages I showed you earlier to see and measure the impact, the end-to-end impact of tokenizers to real-world applications and to concrete tasks. First, we selected different types of tokenizers. On one hand, token-free method, which is splitting all the text character by character. On the other hand, we learned 12 different subword vocabularies based on 3 algorithms and 4 different sizes, vocabulary sizes, where this subword tokenizer splits the text into the words, where each word can be split in several pieces additionally. So we have now 13 tokenizers. And what we want next is to create 13 appropriate language model, general language model. And we took transformer encoder model, BERT-like architecture, and pre-trained it on large text using masked language modeling task, which is a really simple idea. So when you have a sentence, you just hide several words and let the model to guess them. That's it. This is how the models learn general language patterns. And finally, we took these 13 language models and fine-tuned them on these 4 Georgian tasks. Namely, those are text classification, where we used sentiment analysis and toxicity detection. In text classification, the model guesses and predicts if the text is abusive, let's say, in case of toxicity detection. In sentiment analysis, it detects positive, negative levels. For token classification, we used part-of-speech tagging and named entity recognition. So in this case, the model tells us something about each word. In part-of-speech tagging, it can say that this word is noun, or maybe adverb. Which grammatical part is it? In case of named entity recognition, the model can find all the names of cities, person, or maybe company. So in the end, we measured the performance and looked at the results. And we observed that all the subword tokenizers outperform token-free method. While all subword tokenizers, there is no big difference in subword tokenizers. So this means that you can use whichever subword tokenizer comes with your model you are trying to train. Regarding vocabulary sizes, we see that larger ones are best for most of the tasks. So for 3 tasks out of the 4, the larger vocabulary sizes were better. But for toxicity detection task, it's vice versa. Smaller vocabulary sizes work best. So here you can see the performance on y-axis and the vocabulary sizes on x-axis. Toxicity detection and sentiment analysis. And additionally, even though it was not our main intent, we established new state-of-the-art on Georgian toxicity detection benchmark. So now let's look beyond tokenizers, because even with the best tokenizers, you can't go far if you have nothing to tokenize. So if you have no data, then you are stuck. And the next challenge we address is the scenario where you do not have any data in the language you are trying to improve. And plus, you have limited computational resources. We address this with zero-shot cross-lingual transfer. Yeah, terms, zero-shot cross-lingual language transfer, but it is nothing more than just using the data from another language, borrow it from another language if you do not have in your. That's it. And zero-shot means that you have no data at all. And parameter-efficient tuning that says that, okay, if you do not have enough power, computational power, then train fewer parameters. This is that simple. And on this slide, we will compare brute force method, brute force fine-tuning method, which trains all the 100% of parameters, with parameter-efficient method, namely soft prompt, which trains less than 1% of all the parameters. And on the figure here, you can see that this is the architecture, right? You have the text, you input it, it is then embedding, input embeddings, and then it goes into the model. The top block is the language model. It's a pre-trained language model. And during training, all of it is on fire. It is training, updated every parameter there. But in the second case, in soft prompt tuning, all of it are frozen. Instead, you append several random tokens to the input embedding, and you train all of this. This is called soft prompt. These several tokens, colorful tokens, are together soft prompt, which is the same across all the input texts. Now let's move to prompt encoder. So if previous slide was about soft prompt, this is architecture for soft prompt encoding. And it's really just another additional layer before soft prompts that is generating them. The prompt encoder is generating soft prompts. From pseudo prompts, we encode soft prompt. And that's it. This is what we take and apply through several languages. We train the same prompt encoder on several different languages. And those languages are teacher languages or source languages or these other languages I mentioned earlier. And we're doing it in order to improve our language or low resource, some target language. We call this setup cross-prompt encoder, and the intuition behind it is that an additional mixing layer should lead to more generalization. Okay, generalization is good. But what about language-specific adaptation? Can we leave the room for it too? And as a solution, we integrate a hybrid version of standard soft prompts and prompt encoders. And you can see here that first part of this soft prompt here is trained directly and updated directly. It's on fire, yeah? But the second part is encoded through this encoding layer, and yeah, this is called, we call it the dual approach, and the intuition is that by reducing shared layer, we leave more freedom for specific adaptation. That's it. And we evaluated our approaches across 200 languages on topic classification task. We also already mentioned the learning setup, zero-shot cross-lingual transfer. And as a base model, we took already pre-trained multilingual transfer encoder, which has more than 500 million parameters, but I will remind you that we trained less than 1% of it. And it's important that this language model is pre-trained on 100 languages only, while we evaluate 200 languages. So part of it is seen and known by the model, and another one is unknown and unseen. So yeah, here also are the several models we compare with. ChatGPT 4, of course we are not fine-tuning it, so it's 0% of parameter tuning, and others. So what we observed is that XPE is best for most challenging scenarios when the model does not know the languages. So for unknown challenging languages, the XPE works best. For known, well-known languages, standard soft prompts are working best. And dual approach is better for most of the languages, and this is great because our intuition was correct. XP shines when you need more generalization, because when you do not know the languages at all, you should generalize across the languages. But when you evaluate the languages which was known by the model, so you need there to memorize cues, language-specific cues. That's where standard soft prompt shines. And dual approach applies broadly because it balances both strengths. That's it. So in the end, our approaches are outperforming all the others, and that's it. Our research are already published through the peer-reviewed venues as two different separate papers. You can see the titles here and the links also. Thank you for your attention. Keep in touch. Yeah.